So if you think of ds as an infinitesimally small piece of arc length, and you add all the possible ds's, that's kind of like what the integral means, although it's not really. It's really if we were really going to show the power of the math behind it, it would involve the limit of a Riemann sum, wouldn't it? But intuitively, the reason why this notation was developed is so we could think intuitively. If you took the sum, which we kind of think of the integral notation as representing, if you took the sum of all the ds's, all the little subarcs, infinitesimally small subarcs between r of a and r of b, then wouldn't that give us the length of the curve? So that's how to remember it and think of it intuitively. All right, now, what are we going to do then in this section? We're going to think of the ds part as the differential in our integral. And we could rewrite then this using a new notation. And the new notation would then be the integral, we'll call it the integral over c, the curve c, ds. But then what have we done with all the other integrals when we looked at area elements, the differentials as acting like area elements or volume elements? Were we satisfied with just integrating one ds? No. What do? We stick a function in there. We don't even care if it means anything. We stick a function in there and we make a new integral because it's fun. Now, it does mean something, and it's actually pretty powerful math and physics it actually relates to a lot to. But yeah, let's stick a function in there and call it a line integral, even though we're integrating over a curve. So why don't we call it a curve integral? I don't know. It's called a line integral for whatever reason. The curve that we integrate over doesn't have to be a line, but we call it a line integral. So here we go. Here's the idea. Stick in a function. Why not? Sounds like fun. So here's the formula then. We would write it like this symbolically. The integral over c of f of x, y, it could just be f of x, y, but we'll stick in a third coordinate. It could have three components. F of x, y, z ds. Okay, so we're sticking a function in there. So it doesn't represent just the length of the curve anymore. It's going to represent something else depending on what the function represents. And what does that look like? Well, the computational formula then we use, we write the integral from a to b of, okay, to compute what this represents, we're going to have to write x, y, and z in terms of t. We're going to have to parameterize the function in terms of t to get a single variable. And then remember what ds is. It's magnitude r prime of t dt. So this is the computational formula, and it really does look like we're just, well, this is really what we're doing. We're sticking a function into the arc length formula, okay? And that is the computational formula. This is the nice way to write it if you just want to represent an integral and not use as much symbolism. Okay, so what's the assumption for all this to work? The assumption is that C is a nice smooth curve, or it's piecewise smooth, which means it's stuck together. Maybe it has some sharp corners in it or cusps, but in between the cusps you have all smooth curves. Okay, so C is smooth. Or piecewise smooth. And remember what that means to be smooth, which you may not because it's been a while. That means that r prime of t, if r of t represents c, r prime of t does not equal the zero vector, which means you can't have all three components equaling 0. One or two of them can equal 0, but not all three. And of course, it's continuous, and r prime is continuous. And that basically what that does is ensure that you've got a very well-behaved function. In this example, we want to evaluate the integral over c of 12x ds, where I should have written, let me make a little bit of room here. Our curve C is actually going to be composed of two subcurves, C1 and C2. So the notation we could use for that is C equals C1 union C2, where it's defined using this picture. C1 is the green line here, given by y equals x. And we're combining that with C2, which is part of the parabola y equals x squared. And so you can think of, if you were to traverse C, which is the union of the curve in green and the union of the curve in red, you can think of the curve being traveled, so you can see the orientation indication. You would start maybe at 0, 0, and then travel around like so. And you could end up back where you started if you go far enough. Okay, so we're going to want to find then the integral of 12x, that's our function, ds over c. So the thing is, this curve is not quite smooth. It has sharp points at 0, 0, and where y equals x and y equals x squared intersect, which is 1, 1. Does everybody see that? So as you might have guessed, if you want to take the integral over c, where c is piecewise smooth, it has pieces that are smooth, but not all smooth, then you might have guessed that the value of the integral of c1 union c2 then, because that's what c is, right? Of whatever f is, ds, you could break it up into two integrals. You could integrate over one curve at a time and add. And that shouldn't come as too big of a shock based on all your experience with integrals. So the integral over c1 union c2 would be the integral over c1 plus the integral over c2. Okay? In other words, integrals are additive. They've always been additive. There's no reason to expect this to act differently. Okay, so how do we evaluate it? Well, we've got to parameterize, excuse me, we've got to parameterize these curves. So let's start with C1. So C1, remember, is given by y equals x. That's the curve in the picture. It's in green. Okay, how do you parameterize a function? Y equals f of x. You do it the same way every time, unless there's some extenuating circumstance. If y equals f of x, you let x equal t, right? If it's x equals f of y, you let y equal t. And so this one we could actually do either way, but we're going to let x equal t here. Okay, so you could say, you could do this different ways. Your parametric equations then would be x equals t, and since y equals x, y equals t. Or since the formula is in terms of r, then you could say r of t is equal to ti plus tj. And then think about it. If you think of the curve in green starting at 0, 0 and ending at 1, 1, what would be the bounds if this is your parameterization? And parameterizations aren't unique, but this would be the simplest one I could think of. What would be the bounds on t? If you want to start at 0, 0 and end at 1, 1, that's what the orientation indicates, right? 0 to 1. Because if you plug in 0, you end up at 0, 0. If you plug in 1, x equals 1 and y equals 1. Does that make sense on how to find? You got to find the bounds on t because those turn out to be your limits of integration. Okay? Does that make sense? All right, since we're here, let's contrast that with C2, and then we'll worry about integrating in a second. C2 then, in rectangular form, is y equals x squared. So then what's the trick for coming up with your parameterization? What are you going to let x equal? T, because it's y equals a function of x. So you let t equal that x, or x equal that t. And then automatically then, what's y equal by plugging back in? Y equals t squared. Or if you prefer, r of t is equal to ti plus t squared j. And here, I'm going to show you a trick that not every teacher will show you, but this is going to make your life easy. Notice I created this parameterization not so I would start at 1, 1, but that's kind of how you'd think it would be, right? How you'd want to parameterize it, because you're going to start at 0, 0 and end up at 1, 1, and then maybe you'd want to start at 1, 1 and travel down the curve in red. But it turns out that it doesn't actually matter that you go in the direction of orientation for a line integral. This is called a line integral with respect to arc length. For a line integral with respect to arc length, really doesn't matter if you go in the direction of orientation. So you go with the easiest parameterization you can think of. It really doesn't matter which direction the curve is traversed in. Now later on it will matter when we talk about a line integral of a vector field. So keep that in mind. So what would t then have to run from with the parameterization that we've come up with here? Well, yeah, I guess we'll start from at 0, 0 and end up at 1, 1 again. So 0 to 1. And verify. When you plug in 0, does 0, 0 pop out? Yep. You just want to make sure that you're going to cover the entire curve in red when t goes from 0 to 1. And when you plug in 1, does 1, 1 pop out? Yeah, 1, 1, and then 1 squared is 1, yeah. Okay. So then we're just going to individually compute the integral over c1 and the integral over c2, add together, and we get our answer. Okay, so the integral over c1, remember the integrand is 12x. 12x ds is going to be, okay, we need to think about this. What is ds equal to? Remember, ds is equal to the magnitude of r prime of t dt. So computationally, you're going to need to find that, because when you use the computational integral, it's just like using the line integral formula, except you have this extra 12x in there. That's the function f of x, y, z, which is just in terms of x in this case. So it's going to be the integral from a to b, which is 0 to 1, of 12, what's x in terms of t? T. 12t, and then magnitude r prime of t is what comes after that. I'll put that into the next step, but I just want to remind you that it has to be there, and then the dt. So you're going to have to compute this magnitude r prime of t dt just as if you're finding a length of a curve, like you did back in the second chapter. But that's easy enough to do, isn't it? I'm going to stick the answer right in here. It's just essentially well, you have to take the derivative, and then it's essentially the magnitude, right? So the derivative, maybe I'll show that step for you. What is couple of things. So ds is magnitude r prime of t dt. Okay. And then what is r prime of t? It's 1i plus 1j, right? Taking the derivative of this guy. Everybody agree with that? Okay. And then what's the magnitude of it? Root 2. Square root of 1 plus 1, which is root 2. So then our integral over c1 becomes just the integral of 12t times the square root of 2 dt. Not too bad, right? So I can pull out a 12 root 2 in front, and then I'm integrating just t dt. What's the integral of, God, we haven't seen an integral this easy in a while. I don't know if I remember how to do it. That's on the exam? All right. So it's t squared over 2, right? Evaluated from 0 to 1. Notice I put the denominator 2 out here. So we just get what? 6 root 2? But we're not done, are we? That's just the integral over C1. And concurrently, I'm going to compute the integral over C2. Now we need, so that means we need R prime and we need magnitude of R prime to stick in our integral. So what's, for now looking over here at our R of t for the curve C2, what's R prime of t? Not quite as simple, is it? It's I plus 2tj, right? And then what's the magnitude of that beautiful thing? Square root of 1 plus 4t squared. Would you buy that? Okay. So remember then the integral over C2, symbolically it looks much the same, right? But when you plug in the details, it will look different. It'll be the integral from, it happens to be the same, the way we parameterized it, the same limits. And then it'll be a 12, which we can put on the outside right away if you want. What's x in this case? It happens to be the same, but then it changes. ds is going to be magnitude r prime of t, which is square root 1 plus 4t squared dt. Okay? Is this too, okay, this isn't so bad, you guys. I can pull out a 12, and then I have t times the square root of 1 plus 4t squared. What technique do I use to integrate this? U substitution. U would be what? 1 plus 4t squared. So what would du be? Okay, so I need an 8t out there, which means I multiply by 8, I better divide by 8. So now I can integrate this as just u to the 1/2 without actually making the substitution. So I don't have to change the limits of integration. Okay, what does this become out in front? 4 into 12 goes 3 times, and 8 twice. Okay. And then what does this become? 1 plus 4t squared is our u. So it was u to the 1/2, so it becomes u to the 3/2, and then times 2/3. Evaluated from a nice 0 to 1, but you do have to be careful here. So you'll have a 1 out in front for now, right? Or a 1 out in front. And then if you plug in 1, what do you end up getting? 1 plus 4 times 1 squared to the 3/2, right? So what is that? 5 to the 3/2? But then when you plug in 0, you get something that's non-zero, right? Which would be minus what? 1. Okay, so let's put it together then. The integral over c, which is the union of c1 and c2, of what was it, 12x dx, so symbolically this is what we are finding, right, is going to be the sum of these things that we just found. So 6 radical 2 plus, I'm going to write 5 to the 3/2 is 5 root 5 minus 1. Okay? There you go.